When I first started practicing for system design interviews, every tutorial jumped straight to microservices. I didn't know where to actually start or when I'd actually need microservices. So let's fix that. Every system design starts here: a user, an application, and a database. This is a monolith, one code base that does everything: your UI, login system, notifications, backend logic, all in one place. When traffic grows, you scale horizontally. Clone your application across multiple servers. Add a load balancer to distribute traffic. Now you can handle more requests. But notice that they all still talk to the same database. You've just kicked the problem down the road. You can scale app servers infinitely, but you still have one database. So we optimize, add read replicas. Data gets copied to replicas that handle reads, which is usually the bigger volume. Writes still bottleneck on the primary, but you've bought yourself headroom. You can then add caching, Redis or memcached in front of your database. This is oversimplified, but it's a good mental model. Here's your scaled monolith: load balancer, multiple app servers, caching layer, database with replicas. This architecture powers billion-dollar companies. GitHub ran on this for years. Stack Overflow still mostly does. It's not a beginner pattern, it's proven and production ready. So, why would anyone want to move away from this? Two reasons: organizational scale and technical scale. Organizational one is the one people miss. As teams grow, productivity drops. It's called the Ringelmann effect. Communication gets harder, accountability gets fuzzy. Amazon recognized this early with the two pizza rule. No team should be larger than what two pizzas can feed. But you can't have small autonomous teams if everyone shares one code base, one deployment pipeline, and one database. As your app grows, the single code base becomes unwieldy. One team's bug can block everyone's deployment. Microservices give you boundaries. Each service is independently deployable. Each team owns their service end to end. Services communicate through API contracts. Each can have its own database, tech stack, and deployment cadence. The profile service needs caching, use Redis. Photos need blob storage, use S3. Microservices give you that freedom. But that flexibility comes at a cost: latency. In a monolith, when users need profile data, it's a function call, microseconds. In microservices, that's a network call. Serialization, transmission, deserialization, we are talking 10x to 100x slower. Add an API gateway for auth and routing, it's another hop. This isn't a flaw, though, it's a trade off. Teams manage it with caching, connection pooling, async queues, and smart service boundaries. Now, the hardest problem: distributed transactions. In a monolith, transactions are simple: lock inventory, reduce stock, charge payment. If anything fails, you can roll it all back. It's one database with full asset guarantees. In microservices, it's not so simple. Your order service has its own database, inventory has another, and payment talks to Stripe. There's no single transaction wrapping all of this. What happens if payment succeeds but inventory update fails? What happens during a network partition? This is the distributed transaction problem. There are no automatic rollbacks. These are literally separate systems. Maintaining consistency requires careful design. You need idempotency. Every operation should be safe to retry. You need to use idempotency keys so retrying decrement inventory doesn't decrement twice. You need retry logic to handle transient failures. And you need good observability to debug when things go wrong. It's a trade off. You lose transactional simplicity, but gain independent deployability and scale. Here's the mental model. Monoliths are simple, fast, and proven. Start here. Microservices trade latency and simplicity for organizational velocity and independent scaling. In interviews, don't just explain the pattern, explain the trade offs. That's what separates senior engineers from everyone else. Now, how would you apply these concepts to a system like Ticketmaster? How do you prevent two customers from booking the same seat? It's a classic distributed transactions challenge and one of the most common system design interview questions. You can practice solving it on Peppermint AI. Link is in the description.